Um, okay, I believe we can start now. I'm going to record.
Shall I get started?
Yes, yes.
Excellent. Well, thank you so much for the kind invitation. It's an honor for me to be giving this Zoom series of lectures. I would love to be there in person. So next time, if you organize an event in person, please, with no doubt, invite me.
Fantastic. Fantastic.
Thank you. You can take my word for it. Okay, so this is a series of 3 lectures. It will be kind of a full lecture divided in 2 because I teach today in the my course here at Harvard. So we will go over different topics. We will try to cover the following topics. First, we will go through the hypothesis of. Do you read when I write here? Hypothesis of ergodicity. This is what we will try to cover. We will try to cover Gaussian random fields, hopefully this morning. Then we will go over correlation functions. And power spectrum. Survey geometry. Bayesian and frequentist interpretation of probability. Bayesian and frequentist interpretation of probability, likelihoods, and modeling of data and statistical inference. So those are the topics that I want to cover. If we have time, we will go over Markov chain Monte Carlo, likelihood analysis, Fisher analysis. This is only if we have time. And new statistical methods that I have been developing with my group in order to analyze cosmological and astrophysical data sets. So this is, again, a series of lectures in statistical methods in cosmology. So I will start from the beginning, okay? I will not be giving a rigorous introduction to the topic. The goal instead will be to give you enough information to start building the general picture of cosmological data analysis, okay? And hopefully this will be fuel for you to want to find out more. So you can always reach out to me, to my email, if you have questions that you cannot ask along the course of these 3 hours or 3 or more hours that I will be talking today, okay? And I should say that these lectures are based on a number of reviews and papers. I will write them here, so in case you have more questions and you want to find out more, okay. So, yeah, number 1, the bibliography, some useful bibliography, So I have a list here, not in any particular order. There is a book by Robert Lupton called Statistics in Theory and Practice. Let me write it, Statistics in Theory and Practice. This is a book. It's from 1993, so already old, by Robert Lupton. There is also another book that I recommend, which is called Advanced Theory of Statistics. Advanced Theory of Statistics. This book is by Stuart and Ord, and it's from 1994, probably. Many of you were not even born then. This is by Stuart and Ord. And there are papers. So there are some papers. There is a paper called Bayes in the Sky, Bayesian Inference and Model Selection in Cosmology by Robert Trotta and collaborators. The archive number is 0803. Let me write it here. Another paper is by Licia Verde and collaborators. It's called Statistical Methods in Cosmology. The archive number is 0911-3105. Okay. Obviously, there are many more references on the topic, but I just thought I would tell you about some in which these lectures that I wrote are based. Okay. Okay, so let's start from the beginning. Let's start from the hypothesis of ergodicity. And what do I mean by this? Hypothesis of ergodicity. Ergodicity. Right. So basically what I mean by this is that when we are comparing the results of theoretical calculations to the observed universe, we don't focus on the density contrast of matter, for example, at a particular point in space. Instead, what we do, so we don't compare our theory with a particular point in a particular region of the universe, right? Instead, what we do is we predict the average statistical properties and compare with our model. And additionally, we consider that the universe we live in is a random realization of all possible universes that could have been a realization of the true underlying model. So all the possible realizations of the true underlying model make up an ensemble. Okay, so we think about our universe as one realization of the ensemble of many possible universes, okay? And so one assumption that we made for standard cosmological analysis is that the part of the universe that we are observing, that the part of the universe that we can observe, is a fair sample of the whole universe, okay? So this is, so we make the assumption that our observed universe is a fair sample of all the possible universes, okay? So when we derive, for example, the parameters for our model, we are assuming that the measured parameters in our patch of the sky are a fair sample of the parameters of the whole universe, okay? This is very closely related to the so-called cosmological principle. This is the fact that the statistics of the universe has to the statistics of the universe has to be considered as an average over the ensemble, okay? But in cosmology, the problem is that we have one universe. We cannot repeat the experiment and restart the Big Bang, okay? So what the fair sample hypothesis, I will write some words here. What the fair sample hypothesis states is that what the fair sample hypothesis states is that samples from well-separated parts of the universe are independent realizations of the same physical process, okay? So samples of well-separated parts of the universe are independent realizations of the same physical process. You see, instead of measuring different universes, which we cannot do, we say, well, if I measure different samples in different parts of the universes, those count as my samples from the ensemble of the distribution coming from the true model, okay? So the hypothesis of ergodicity says that averaging over many realizations is equivalent to averaging over large enough volume, okay? And so basically the cosmological field we are interested in is just a realization of a statistical process. So let me write this down. The hypothesis of ergodicity, what it's saying is that averaging over many realizations, which is what we would like to do, but we cannot do because we don't measure many realizations of our universe, but that we assume that is equivalent to averaging over a large enough volume. See, we are using the fact that our volume is so large, the measured volume is so large, that if we measure different parts of the observed universe, this counts as realizations of different universes. That's the hypothesis of ergodicity, and that's a crucial hypothesis when we are doing in standard cosmological analysis, because again, cosmology is very particular. In cosmology, we are just measuring one universe. It's one of the few cases in which, if not the only case in physics, in which we cannot rerun the experiment. Okay, we cannot say in general, what you do is you rerun the experiment, you have many realizations of your same experiment, you model the noise, and you can compare it with the data and assess the significance of the model that you're considering. But in this case, we just measure one universe. So any questions about this? By the way, I will not be looking at the chat. So if you have questions, please just feel free to interrupt and ask questions. Okay. Let me move on to another. I will be introducing the hypothesis of ergodicity and different concepts that then will be useful for learning how to analyze cosmological data, okay? So the next concept I want to introduce is the concept of Gaussian random fields, which, of course, if you are physics students, this will not come as a really new concept, but this is an important concept that we use over and over again in cosmology. So let me introduce the second concept that I wanted to talk about, which is the concept of Gaussian random fields. I will be lazy and call it GRF in my notes, okay? So, okay, so basically, Gaussian random fields are very commonly used in cosmology, and they have several advantages, okay? There are strong motivations from inflation to assume that the primordial fluctuations that gave rise to the present-day structures follow a Gaussian distribution. And the main advantage is that it is possible to compute their statistical properties analytically, okay? Basically, the mean and the covariance of a Gaussian random distribution completely defines the Gaussian distribution. So we will be focusing here on density fluctuations. And the distribution of density fluctuations, matter density fluctuations or galaxy density fluctuations, cannot be exactly Gaussian. Why do I say this? Let's write density fluctuations. So we will be focusing on density fluctuations, okay? And the density fluctuations, I will call them delta, will be defined as delta rho over rho, okay? These density fluctuations are delta rho over rho, delta rho over rho. What is delta rho? Is the matter density, say we're talking about matter, the matter density at a particular point in space minus the average over the average, yeah? That's delta. And this quantity, you can see already that this quantity has to be greater or equal than -1. So greater or equal than -1, okay? So you can see that if this quantity is greater or equal than -1, you know, if you're very close to -1, you cannot, the tails will be cut. So the distribution will not be Gaussian, okay? It doesn't go, it's not symmetric around -1, for example, if it always has to be greater or equal than -1. However, if the density fluctuations are small enough, the approximation that the density fluctuations are Gaussianly distributed is a good approximation, okay? So if delta is very close to 0, then the Gaussian approximation is a good one. Okay. Now, if the density fluctuations are a Gaussian random field with average 0, then the probability distribution function is given by the following. So if delta is a Gaussian random field, let me write this delta a little bit better, but if delta is a Gaussian random field, we can write the probability distribution function, okay, the probability distribution function of delta as a Gaussian random field. Okay, so probability distribution function will be minus e to the -1/2 delta transpose covariance to the -1 delta over some normalization factor, okay? And this normalization factor is 2 pi to the n over 2, where n, I'll define what n is, times the determinant of the covariance to the 1/2, okay? So delta is a vector, okay, at different points, given by delta 1, blah, 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 until delta n. And C is the correlation matrix, or it's actually the covariance between the deltas, okay? And C, ij, is equal to delta I, delta j, okay? And it's also known as the correlation function. I will write it as Ri minus Rj, okay? So delta 1 or delta 2 is delta evaluated at position at R1, delta 2 is delta evaluated, okay? So delta 1 here means delta evaluated at position R1, delta 2 is delta evaluated at position R2, and so on. Okay. And so when we start talking about Gaussian random fields, an important property of Gaussian random fields is that the Fourier transform of a Gaussian random field is a Gaussian random field, okay? It's Gaussian. And so what it means is that, you know, either in real space or in Fourier space, the PDF of the density fluctuations at any point in space is Gaussian, okay? Is this clear? If this is clear, yes? Sorry.
Yes, it's clear.
Okay, excellent. If this is clear, let me move on to the next item I wanted to cover, which is correlation functions and power spectra, okay? Basically moments and cumulants. Okay, good. So we are continuing to make assumptions, but I think it's, I mean, it is a good way of learning first to learn it is important to first learn the assumptions that we are making, and then we can start playing with the different concepts. But first we have to be clear about the assumptions. They have hypothesis of ergodicity. We will be making for now, for a very brief period of time, the assumption of a Gaussian random field, and then we will move on to add non-Gaussianities, okay? So, okay. So the next concept that I want to introduce is the concept of correlation functions and power spectra. My handwriting is getting worse and worse. And power spectra. Great. Okay, so let me write down some of the basic expressions for the correlation function and power spectra, okay? So that we can move on from there. So I will define a universe that is a cube of volume V, because things get simpler with periodic boundary conditions, and then we can take V going to infinity and the volume of our universe, or you can then consider that the volume is just very large, okay, and that will be our universe. So let me first start from the basics, so that we are all in the same page, okay? So the Fourier transform in general of a function f of r, okay, the Fourier transform in K space is given by the following. This will be our convention for Fourier transform, where we are integrating over real space of f of r, the vector, and we are here e to the I k r, okay? The convention will be like this. So therefore, if we are considering a universe with volume V, f of r will be given as 1 over V, the sum, this is a discrete sum over wave numbers, okay, of the Fourier transform of f times e to the minus k dot r. Okay? Okay. So now our functions will be delta and delta. We will consider delta of r and the Fourier transform, which is, but this is not a tilde, sorry. The Fourier transform of delta, okay, which are typical quantities considered in cosmological analysis. Okay, so the correlation function, we can write the correlation function, which is the 2-point function of the density fluctuations in real space, okay? The correlation function, let's write it as r minus r prime here, will be given by the average of all the configurations of the random field that we are considering. So the average of all the configurations of the random field that we are considering can be written in the following way. This is delta r, and this is delta r prime, okay? Now, this is the correlation function that we can defined from our theory, and we take the average over all possible configurations of this random field. But for a single realization, okay, if we go and measure the correlation function of our universe, we can define an estimator of the correlation function, and this estimator of the correlation function will be the spatial average over separated points, pairs, by some chosen distance, okay? So okay, let me write down. This is the average over all configurations. This is the average over all possible configurations. But for a single realization, we can define an estimator of the correlation function. And the estimator of the correlation function will be given as the spatial average over pairs separated by some distance, okay? For estimators, I will be using the notation of a hat on top of the quantity that I want to measure. So the estimator of a correlation function will be denoted like this, okay? This estimator of the correlation function will be given by what? Basically, I am integrating over pairs, delta R, delta R plus R prime, okay? I'm integrating over all possible pairs, and then I'm dividing by the volume, okay? So here we are using, we are assuming translational invariance, okay? We are assuming that the correlation function only depends on the distance between 2 points, okay? If not, I would have, here, by the fact that the correlation function just depends on the distance between 2 points, I'm assuming that there is translational invariance, okay? If not, I would just have the correlation function of this point and this point, okay? The correlation function would depend on 2 positions, not just one distance. Okay, so the true correlation function is the expectation value of the estimator for the correlation function. And this is because the estimator of the correlation function that I just wrote here is defined to be unbiased, okay? So you can write the average of the estimator of the correlation function. This is what? This is 1 over v times the integral d3 r prime of the average of delta r plus r prime. Okay, but this is the correlation function of r, right? And so this integral will be giving me a factor of a volume over volume. It cancels out. So this is equal to delta of r. Great. This means, well, this is of the distance, right? This is of the distance, this is of the distance, this is of the distance between these 2 points. This means that the estimator for the correlation function is unbiased, okay? So the average, the mean value of that estimator is actually the correlation function. Good. If we were not getting the correlation function, this would mean that our estimator has a bias, okay? If I told you that the estimator is 2 times what I wrote here in this equation, then this would be biased, and I would not be getting, I would be measuring in the data something that cannot be compared directly to our model of the correlation function. Okay, The same way we define an estimator for the correlation function, we can define an estimator for the power spectrum. And the estimator for the power spectrum can be defined in the following way. I will use the hat notation again, okay? And this will be given by 1 over V, delta K, delta K prime, okay? Great. Okay, with a conjugate here. Whoops, sorry. Let me add a conjugate here, okay? And so you can show that the expectation value of the estimator for the power spectrum is actually the power spectrum itself, okay? So the estimator for the power spectrum is unbiased, okay? And you can also show, well, this is equal, so, okay. So this, the expectation value of the power spectrum will be given by 1 over V, the expectation value of delta K, delta conjugated of K prime, okay? And this is equal to the integral of D3R, the correlation function, e to the IKR, delta K prime, where this is just the delta Kronecker. Okay, what I want to show you here is that, okay, good. So I told you that I want an unbiased estimator for the power spectrum. So this means that this will now be our power spectrum. So our power spectrum is given by this integral, which it's quite interesting. This may sound like an obvious statement that the power spectrum is the Fourier transform of the correlation function, but it didn't have to be necessarily the case, okay? We started with the Fourier transform of our density field, okay? We defined the estimator for the correlation function, and we saw that actually the two-point function in Fourier space, which is the power spectrum, is the Fourier transform of the correlation function. So again, the power spectrum is the Fourier transform of the correlation function, which is not an obvious statement, if you think about it, from before, okay? And you see that this over here, we end up with the delta Kronecker of KK prime. This is a consequence of translational symmetry, okay? The fact that we have translational symmetry gave us this delta of KK prime. And so when we go to infinity, or when we go to a very large volume, we can, so when going to a large volume, we can just take 1 over V times the sum over the different wave numbers. This will go to 1 over 2 pi cubed times the integral over D3K, okay? All right, so what happens here? What are the Gaussian random fields? So the phases of the Fourier modes are random, okay? And the real and imaginary coefficients of those are Gaussian distributed, okay? And so if that is the case, if the field is Gaussian, is a Gaussian random field, the power spectrum completely specifies the field. You know that if a field is Gaussian, all of the information is contained in the power spectrum, right? However, we know that unfortunately, or fortunately, because it makes things more fun, due to gravity, the galaxy density field is highly non-Gaussian, okay? This regardless of what we assume for the initial conditions of inflation, even if the initial conditions were Gaussian, we know, and it's not exotic physics, it's actually physics that we observe, we know that due to gravity, the large-scale structure of the universe will end up being highly non-Gaussian, okay? So at megaparsec scales, clusters are over densities of order 1,000. And since we know that the density field has to be, the density fluctuations, the perturbations have to be greater or equal than -1, you know, we know that there are no delta of -1,000 in the universe. So these regions are highly non-Gaussian, okay? So clusters, for example, let me write this down, at megaparsec scales can have density fluctuations of order 1,000, but we know that the density fluctuations have to be greater or equal than -1. Therefore, the perturbations, density fluctuations of -1,000 don't exist, okay? Therefore, the field is highly non-Gaussian. And this is interesting because this is telling us that we need to move on beyond the power spectrum, okay? The power spectrum doesn't contain all of the information. So the question is, how do we specify a non-Gaussian distribution, okay? How do we specify a non-Gaussian distribution? Who can tell me? No? Have you probably, perhaps in other lectures, you already saw that you can move on to higher order correlation functions, okay? Higher order correlation functions can be used to learn about non-Gaussianities in the field. And this is a big topic in cosmology, okay? Not only primordial non-Gaussianities, that are the non-Gaussianities coming from physics of the very early universe, the physics of inflation, perhaps under the theory of inflation, but non-Gaussianities actually coming from gravity, okay? Okay, so what do we need to do? We need to move on to higher order point functions, or we could use other statistics. For example, with my group, we have been working hard on the wavelet scattering transform, which is a method, a statistical way of analyzing data in which you can extract non-Gaussian information. But let me give you the standard way in which the field has been moving over the past tens of years, perhaps 20 years. I'll give you the standard way in which the field has been moving, and if we have time, we will talk about other statistical techniques, okay? So we will define, okay, so we will define central moments as the following. So central moments are defined as follow. Let's call it mu m. You will see, I will numerate them, but this is the average over, you know, x minus x average to the m, okay? Where the average, what do I mean by the average? The average is defined as follow. So let's take the average of f of x. Okay, the average of a function will be defined, you know, you all probably know probability and statistics is defined over the integral of f times weighted by the probability distribution, right? So dx, f of x, and times the probability distribution of x, okay? So what is mu2? For example, I said mu2, but I write mu1. Okay. Mu2 is the variance, okay? It's known as the variance. You take x minus x squared, take the average, that's the variance, okay? Mu3 is the skewness, mu4 is related to the kurtosis, and so on. Mu3 is the skewness. Mu4 is not the kurtosis, but is related to the kurtosis, and so on, okay? And so all the moments can be, you know, okay, so let me actually start from Gaussian fields, okay? So for Gaussianly distributed fields, the cumulants are 0 for odd order point functions, okay? So only the even point functions survive, okay? So for Gaussian random fields, only even order. Sorry about this. This iPad is new and I'm even order point functions survive. Is this okay? Yeah. Meaning is non-zero, okay? And all the moments are specified, and all the moments are, this is Gaussian random fields, are specified by mu1 and mu2. Mu1 and mu2, okay? So what are the moments? What are the moments? We can convert from moments to cumulants, okay? So the moments, as I said before, are given by mu2. Sorry, what's going on here? Mu2, mu3, mu4, and so on. These are the moments. The cumulants are given by K2, K3, K4, okay? These are the cumulants. You see that the fourth order moment is related to the kurtosis, but it's not exactly the kurtosis. These are cumulants. Okay, the cumulants are the K's, Ki, I will put here, and the moments are the mu's, mu I. What is a cumulant? So cumulant of order 2 is just, for example, I take K2. What is that? This is x1, x2 minus x1, x2, okay? This is a 2-point function. The cumulant of order 3, let me write it here. I'll not write all the cumulants because it becomes more and more involved, but let me write the cumulant of order 3 here is x1, x2, x3 minus x1, x2 times x3 and all the combinations, right? Minus x1, x3 times x2 minus x2 x3 times x1 plus 2 x1, x2, x3. This is the type of thing that is better to write without saying because it gets more complicated, okay? Those are the cumulants. Okay, so the cumulants will start being non-zero. So for Gaussian random fields, we only have, you know, cumulant up to cumulant of order 2, then the cumulant of order 4 will be specified by the cumulant of order 2, the cumulant of order 6 will be specified by the others, and so on. And the odd order cumulants will all be 0. They start being non-zero when the field is non-Gaussian. Yeah. Any questions about this?
No, we're good.
Excellent. Well, in the last 10 or so minutes, what I wanted to cover in this, the last topic I wanted to cover in this first lecture, let's see, wow, we covered a lot. So we covered hypothesis of ergodicity, Gaussian random fields, correlation functions and power spectra. And the plan was to finish this first lecture in the morning, and then we will continue in the afternoon, but finish this first lecture by covering survey geometry and pseudo power spectrum. And it will become clear what I mean by this. So this is our first lecture. Excellent. Okay, let me go here. So here we will cover survey geometry. Survey geometry and pseudo power spectrum. And pseudo power spectrum. Yes, it is possible to get the lecture notes. Sorry, I said I was not going to be reading the chat, but I got tempted. Somebody asked if it's possible to get the lecture notes. Totally possible. I can send them when we finish today, all the lectures today. So obviously, because we cannot observe an infinite universe, we will always be observing, surveys will always have boundaries. So, and we need to add these boundaries into our analysis through what is known as the window of the survey, or the mask of the survey. Window or mask of the survey. Okay. Basically, the window of the survey will take values of 0 outside the survey and 1 inside the survey. So for example, say you have, you measure a patch of the sky, okay? You measure a patch of the, sorry, there is some talking in the chat, but okay, I will not be following. So we measure some patch of the sky, and so what this will be saying is that if then we simulate a volume of the universe, but we know that actually we are measuring a particular patch of the sky, we will need to add to our simulation or our theory a mask, okay, where everything inside that mask will be multiplied by 1, and everything outside of this mask will be multiplied by 0, okay? So here by 1 and here by 0, yeah? Because we are just measuring inside that mask, okay? So it's a real space multiplication effect. Basically, the observed, the observed field in real space will be the true field, true meaning true coming from a particular model, okay, times multiplied by a window function, okay? This is the window function of the survey. And in Fourier space, because it's a multiplication in real space, in Fourier space, this will be a convolution, okay? So the observed field as a function of wave number will be the true field from our model, convolved with a window function in K-space, okay? So what does this mean? Well, we need to know the survey geometry, first of all. We cannot guess the survey geometry. This has to be known, given by the experiment, okay? But it is known. We know what we are measuring. And if not, our experimentalist friends tell us what they are measuring, okay? So for wave number, so for modes of the size of the survey, this effect will become relevant, right? For modes that are well inside this mask, okay, for modes that are just inside the mask, that's not really a problem. I'm not hitting the boundaries, but for modes that are of the size of the survey, this will become relevant. And we need to convolve with the window function. So the sharper the window function is in real space, the more it will ring in Fourier space, okay? And this will couple different K modes. And so a common method to deal with this ringing in Fourier space is known as apodization, where the window function doesn't go abruptly to zero, okay? This is just a trick to avoid the ringing in Fourier space. So if this were the window function, what apodization, this is what apodization does, which is it smooths out the borders of the window function, okay? Now, the power spectrum with the window function is called the pseudo power spectrum, and it's not the Fourier transform of the correlation function anymore. So the power spectrum, considering, taking into account the window function, is called the pseudo power spectrum, okay? And this is not, as I told you before, remember that before, because of translational symmetry, we got the power spectrum of the correlation function of the Fourier transform of the correlation function. This is not going to be the case when we work with window functions, okay? So let me take actually the case of the CMB, just because it's a simpler case. It's in 2D. So let me take the case of the CMB to exemplify what I mean by a pseudo power spectrum, okay? For example, an example of the pseudo power spectrum. For the CMB, so for the cosmic, did you have lectures already about the CMB?
Yes. Professor David said a couple of things about it.
Okay. So, you know, in the CMB, what you measure is the temperature fluctuations, right, in the sky. And you can make a spherical harmonic decomposition of these temperature fluctuations, and you get coefficients from these spherical harmonic coefficients that are known as these, in the literature, they are called these ALM coefficients, that are basically taking the integral over the solid angle of the temperature fluctuations in the sky times the spherical harmonic over here, conjugate, okay? But now what we have is, if we are not measuring the full sky, but we are measuring a chunk of the sky, you know, we are taking out the galaxy emission in the middle, you know, in the map. So the map is not perfectly symmetric, okay? There will be point sources, there will be all sorts of things that are removed. The instrument will not be measuring, you know, there will be a fraction of the sky measured by the instrument. So we will have a window function. We will call this ALM tilde, okay? Where we can write this as the solid angle subtended by the pixel times a sum over the pixels of the temperature fluctuation on each pixel times the window function on a pixel times the YLM conjugated, and this runs over pixels, okay? And this is the solid angle subtended by the pixel. Okay. Now the pseudo CLs will be defined as CL tilde will be defined as the power spectrum of the ALMs tilde, which are including the window function. So this is 1 over 2L plus 1, the sum over M from minus L to L of ALM tilde squared, okay? But now the pseudo CLs are not going to be the actual CLs where, you know, CLs are just 1 over 2L plus 1, the sum over M from minus L to L of just ALM squared, which are the ALMs here, the ALMs without the window function, okay? So these two, the pseudo CLs, the pseudo power spectrum and the power spectrum will be related in the following way. The average of the pseudo power spectra will be the sum over L of some coefficient that depends on L and L prime that is coupled to this power spectrum CL prime, where this GL, L1, L2, okay, will be just 2L2 plus 1 over 4 pi, the sum over L3. There will be sums over L's, and there will be the window function in the spherical harmonic coefficients of the window function, and we will have Wigner 3J symbols, L1, L2, L3, 0, 0, 0 squared, okay? Okay, and let me write down that WL is just the spherical harmonic coefficients of the window function, okay? What? WLM squared, and WLM, let me define everything here, is the integral over the solid angle of the window function times YLM conjugated. And if we can invert the G, okay, so we have this relation over here. So if we can invert the G, the G matrix, then, or the coefficient that depends on L1 and L2, then you can know the power spectrum, okay? So we can measure the pseudo power spectra, and if we invert the G, okay, the G is well known if we know the window function. So if we know how to invert G, then we can, from measuring the pseudo power spectrum, we can infer what the power spectrum is, okay? And the power spectrum is nothing more, nothing else than the sum over L prime of G, L, L prime to the minus 1, C, L prime, tilde, okay? So this is what we measure, and this is from our theory model, from theory. So if we know this has information of the survey geometry, okay? So if you know the survey geometry and you measure the pseudo power spectrum, you can infer the actual true power spectrum and compare it to your model, okay? So this is what I wanted to cover today, and today, no, not true, this morning for me before I go teach electromagnetism. And after that, in my afternoon and your late afternoon, becoming almost evening already, I will be covering ways. So I will start with the Bayesian and frequencies interpretation of probability. I will move on to likelihood analysis, and I will start talking about modeling of the data and doing statistical inference. So I will take questions. No questions?
I think there are questions. So I think I'm just going to read out this one. Please, guys, you can begin to type your questions now. I think this person was making reference to the correlation function. So he's asking if the correlation function can be used in determining the distance between galaxies.
No. No, the correlation function is a measure of it's the measure of the density of the 2-point function of the density contrast as a function of distance. But I don't think you can use it. It doesn't depend on the particular distance. It's the average over the 2-point function of the density contrast. So let's say the correlation function is a function of a distance, but you cannot determine the distance from the correlation function.
Okay. I think a question that is very common here is I think people are asking, like, how, to a lay person, what is this really about? To a layman, say to someone who has no idea what the lecture itself is about, to a lay person, what is it really about?
What this lecture is about?
Yes.
This is building up concepts in order to guide you through making analysis of data in cosmology. So I'm building up really the concepts of statistical methods used in cosmology.
Okay. There's another question here. Is there, this is from Embarrassing, is there any other means of finding power spectrum without using the Fourier transform or the correlation function?
Right, you can, well, without using the Fourier transform, I mean, the power spectrum is defined in Fourier space, right? So you can learn about the field. Perhaps the question is whether, the correlation function is defined in Fourier space, but you can learn about the statistical properties of the field that you're measuring in cosmology through other ways. Yes, not necessarily through the power spectrum or correlation function, but you can use other methods. In particular, you can use, wavelets to measure statistical properties of the field. And there are a bunch of other possibility statistical methods that have been developed over the years to learn statistical properties of the field. But yeah, not necessarily the power spectrum you see here. For the power spectrum, here, I'm taking the correlation function and I'm multiplying by this coefficient over here, which is a kernel that I chose, right, for this particular purpose. But I don't need to use that kernel. I could use any other kernel. Wavelets, for example, use other kernels, well, depending on the wavelet, but you can use localized kernels. This is a plane wave, so it's non-localized, but you could use another kernel and you could measure the statistical properties multiplying by another function there. Does that answer the question?
Yes, it does. Okay, there's this one. Is the Gaussian completely accurate for early universe models?
For early universe models, is consistent with observations. Yeah, there is speculation that the field perhaps could be non-Gaussian, but for very early universe, we don't have yet the action of gravity. So the observations are well fitted by the assumption of a Gaussian random field. It becomes, so this stops to be true for late universe, but for very early universe, that's correct. The deltas here, the matter density fluctuations are very small. So the Gaussian approximation is a good one.
Cool. Thank you very much. I think there's a lot of, should I call it, questions surrounding, people want to know if it is possible to get the lecture notes, because I think they're saying it's a lot to take in. So they want to go through the lecture notes.
Absolutely, yes. I will be sending you the lecture notes at the end of the day. And you can distribute it.
All right, thank you very much.
My pleasure. Okay, so I will see you in 3 hours from now.
Yes.
In 3 hours, right? 2 p.m. East time.
Yes, yes.
Excellent. The same Zoom link. I'll see you then.
Yeah. Thank you very much.
My pleasure. See you in a bit.
Yeah. Thank you.
Bye-bye.
Yes.
Thank you. I will run to teach now, but thank you very much.
All right. Thank you very much, Prof. Thank you so much. Yeah. So guys, I'm going to send an email to you guys, a reminder for the lecture. I know it's it's probably a lot to take it. Let me stop recording. I know it's probably a lot to take it. Yeah, and if it is possible, Harrison and Pius Bamigboye, please, you guys should send me. She asked for it, so you guys should please send me this thing. Your, how do you say it? Names or something. Just please send me a DM. Please send me a DM. That will be Harrison and Pius Bamigboye. Thank you very much, everybody, for joining. I'm looking forward to seeing you guys in the subsequent lecture in the next one. Please make sure to turn up. I know I think it's a lot to take in, the equations and all of that. So I don't know, the people in charge of